All right, so we're going to analyze this equation that we derived. Some of it's going to feel a little bit familiar from general chemistry, but that's okay. But it's just going to justify it as a really important tool that we have for us. Remember, we're still dealing with our assumption that we have ideal gases. We'll talk more about breaking that assumption probably in the next video. One little caveat I want to talk about is you might see these represented differently. So the way I wrote them now, and I fall in this trap too, the way I wrote them now is I'm showing you that they're molar quantities, and this is working out unit-wise because remember that R does have a per mole in it, okay? Because these are so common, and you'll see your book do this, like it'll just kind of drop these lines. Every once in a while I do too. And it'll just say, hey, this is so important, we use it all the time, we understand that these are molar quantities, all right? So you just have to make sure the units are working out. A lot of the times the reaction G and the standard reaction Gibbs energy, they're molar quantities, even if they don't have that over bar listed. For example, we know how to calculate these, and I mentioned it even in the last video. We know what you would do is you would go to a table, and in your book you have table 26-1, right? And you would look up a bunch of delta G formations, right? And you would say, okay, this reaction, right, it's G under standard conditions can be made by doing a sum for your products of your stoichiometric coefficient, the formation reaction for that particular species, Gibbs energy, under standard conditions, you do that sum for your products. Like I said, I kind of mentioned this last time. You do the same sort of sum. I'll just change it to a J, different subscript. You do that same exact sum for your reactants. You subtract, right, from all those table values. Hopefully you understand the type of process I'm talking about. We referenced it multiple times this semester. You do that subtraction, and then that's delta G under standard conditions for your reaction, all right? All those delta G's in the table, even though they're just labeled as delta G's, okay, all of them are molar quantities, okay? So again, you just have to pay attention to units. Sometimes we use the overbar. Sometimes it's like, oh, well, we understand that they're molar, so we don't use the overbar. So like I said, just kind of be wary of that. Along those lines, let's try to analyze this now. All right. Remember, even though in general chemistry we talk about things being set up with us, we don't use the word standard conditions. We use the idea that we use atmospheres in KP, all right? That's technically not correct. It's that whole deal where we should use bar. So whenever we use a KP, we should be getting answers out in bar. Now, remember, a bar and an atmosphere, they're really close to each other. We could modify our KP to account for the fact that we've converted from atmospheres to bar. Just remember, like for me, whenever you're doing this, now that we're in physical chemistry, whenever you hear reference to a KP, we're going to put all our pressures in bar so that we make sure that we have that P naught term that's going to cancel in terms of the units. We saw that last time. Now, the reason I bring this up is because imagine that all your gases are at 1 bar. All right, all your gases are at 1 bar. And like I said, we're going to just kind of bring up multiple scenarios, and we're going to analyze what happens to this expression and why it's the starting point for a lot of our analysis. So what if all your gases are at 1 bar? Well, if you think about what happens here, Q, right, remember how we have it set up. Looks like your pressure of your products over your pressure of your reactants. So let's say we still have, let's say we still have products D and C, and we have reactants A and B, right? If all our gases are at 1 bar, right, then we know that our reaction quotient is 1, okay? Now let's substitute that value into this delta G. Well, what's the natural log of 1? The natural log is 0, right? Natural log of 1 is 0. So what we end up with in this instance is we have delta G for the reaction, right, is equal to delta G for the reaction under standard conditions plus 0. But now wait a second, why is this like a good result to get? under these situations where all these pressures, we start off a chemical reaction where everything's a gas and they're ideal gases and everything's measured at 1 bar. Well, that is the definition of standard conditions. So it's really important to kind of realize that, okay, yeah, when I put those values in here and I get a Q of 1, a reaction quotient of 1, this recovers my standard information. So under those instances, right, all I would have to do is look at a table, figure out what delta reaction G naught is with that calculation that we showed earlier. That is the delta G for the reaction as written because everything's under standard conditions. And that's when the sign of delta G naught becomes important, right? Not that it becomes important. That's where it dictates completely, because this term goes away. It dictates completely what happens for the system. Is it spontaneous as written? Is the reverse spontaneous, or is the system at equilibrium? Okay, so like I said, it's important to kind of realize we recover standard conditions when we make our pressures standard pressures, all right? And then delta reaction G naught dictates the spontaneity of that process. And again, we're always going to assume that we're under isothermal isobaric conditions, all right? Let's look at a different scenario. All right, what happens at equilibrium? Well, from previous sort of discussions in the semester, we know that at equilibrium, right, all the mu's, right, are canceling out, right? The chemical potential to be on the reactant side versus the product side, they're equal to each other, okay? There's no net motion. At equilibrium, which is another scenario we run into a lot, all right? Delta reaction G, and remember that's where your chemical potential information is. Delta reaction G, not delta reaction G naught. But your reaction, if it's at equilibrium, delta reaction G is 0. Okay? So that means that 0 is equal to delta reaction G naught plus RT, the natural log. Oh, wait a second. Right? At equilibrium, remember what happens to Q? Q gets relabeled as K. Okay? So we can rearrange this. Delta reaction G naught equals minus RT, the natural log of K. We get this very important result where really equilibrium, no matter what your conditions are set at, all right, initially, no matter what your conditions are set at initially, the way we have the equilibrium constant defined, right, as being the reaction quotient when the reaction no longer has any net movement, K is completely defined by delta reaction G naught. Okay? So you would have to go to a table, figure this out, but once you do, at that table temperature, right, now you know what the equilibrium constant is. If you're away from that table temperature, okay, we need to actually do some work to get what the delta reaction G naught is, just like you kind of did in lab, okay? But if we're at that temperature, all right, that table temperature, this will give us a way to get our equilibrium constant. So our equilibrium constant is defined by delta reaction G naught. So we can have a reaction under non-standard conditions and we still look at, well, what if they were standard? That's what determines what our equilibrium constant is. And it's all here in the mathematics, okay? So then with this as a mathematical formula we can use, let's analyze this in the context of introducing K, because what we see inside here, right, for our delta reaction G, is we see this delta reaction G naught. Oh, well, I can just do this substitution right in there, right? So let's do that. And let's cast delta reaction G in terms of not just Q, but in terms of K and Q. All right, so I'm going to make that substitution there. Delta reaction G is equal to minus RT, the natural log of K. Right? Now this is for any sort of setup we have, any Q, any set of initial conditions. This is always minus RT natural log of K. Right? plus RT natural log of Q, right? Now look at, we can do some natural log algebra like we did on the last video. We can pull out an RT, and then we're going to have as a positive natural log of Q minus a natural log of K, right? And so what we get out is delta reaction G is equal to RT, the natural log of Q over K, using our natural log algebra rules. Okay, so now this is really kind of interesting because Q deals with like your initial setup, like what pressures you actually see possibly away from equilibrium. K is all about getting those pressures to what they have to be, right, to be at equilibrium. So this is one nice and tidy expression that gives us delta reaction G just based off of Q and K, right? And remember, the importance of this is because we're under isothermal and isobaric conditions, this value predicts spontaneity, right? The sign of delta reaction G predicts spontaneity. Not the sign of delta reaction G naught unless you're under standard conditions. We already proved that, right? But delta reaction G predicts spontaneity, right? And we can kind of look at this as a way to sort of test that. So let's test this expression, okay? So what I'm going to write next is kind of underneath this expression here. Well, what happens if Q equals K? What happens if you calculate, right, all your pressures, raised to the stoichiometric coefficients, analyze correctly, right, like we have in terms of the definition of Q, and you get the exact same number that you get for K? Well, in that case, right, what we have is the natural log of 1 showing up here, and the natural log of 1 is 0. So then this whole entire side is 0. And so when Q equals K, delta reaction G is equal to 0. And why is that a great result to get? Why is that an important result to get? Because that tells us we are at equilibrium. Now, the way that we learn it in general chemistry, right, is we just kind of deal with Q and K, and we say when Q equals K, you're at equilibrium. We just use that as a definition. But now, mathematically, right, we see why. Because mathematically, what we get out is the thing that maps on to that second law of thermodynamics, right, it equals 0. And so delta S universe is equal to 0, so you're at equilibrium. Okay, let's do another test. Let's do a test where Q is greater than K, right? Where Q is greater than K. So you look at all your initial pressures, throw them in the Q, calculate a value. You have K that's set for that temperature. K is set for a given temperature. You do this division and you see that Q is greater than K, right? What we have is the natural log, and inside here, right, this number is greater than 1. So I'm just going to write this as greater than 1. It's a natural log of a number that's greater than 1. So when the natural log is greater than 1, right, what we end up with is a positive natural log. We get a positive value out. So this term then is positive. R is always positive. T is always positive. So what we get out is a delta reaction G that is itself positive, right? Now remember what G has to be. How it maps onto the second law is, remember we introduced that sign convention where the reaction gives energy or the process gives energy has to be negative to be spontaneous. Well, here we say, all right, that it's positive. So how do we interpret this result? The reverse reaction is spontaneous. Remember, we could then just flip the reaction. And then flipping the reaction would change the sign of this. It would make it negative, all right? The reverse reaction is spontaneous. Right? The reverse reaction is spontaneous. Now, what did we say in general chemistry, all right? In general chemistry, we said, oh yeah, well, Q has products here and reactants here. And what we said in general chemistry is Q is greater than K. Well, Q is too big. Because remember, K is where you're trying to get to. So then if Q is too big, what has to happen to get to equilibrium? Well, if Q is too big, we have to lower this. And we have to raise this because this is in the numerator, right? And this is in the denominator. So if this goes down and this goes up, Q is going to eventually get smaller and equal K. Okay? And that's the argument that we gave in general chemistry, right? Well, how do you make the products go down and the reactants go up? Equilibrium has to go from products to reactants. Equilibrium shifts to the left side. Now, what did we just show mathematically? We just showed mathematically that the reverse reaction is spontaneous. So what did we write from our general chemistry type analysis? That we should make more reactants. The products should go to the reactant side. The reverse reaction is spontaneous. It comes from the math associated with this analysis here. Okay, so try to make those connections. One last test. What if Q is less than K? All right, you can kind of see where this is going, hopefully. And then I want you to make the connection yourself to what our Gen Chem argument would be. If Q is less than K, let's do an analysis of this math here. The natural log now is a natural log of a number that's less than 1. And so what you get out for this natural log is you get a negative value. And if you're getting a negative value for the natural log, this is positive, so delta reaction G is negative. And what does that tell you? That tells you that the forward reaction is spontaneous. That means as we have it written, the reaction is going to progress to make more product, all right, until we're at equilibrium. Think about how we made Q versus K arguments in general chemistry and link it to this math that we have here, that the forward reaction is spontaneous, because now we're proving that with this expression. So a really important, interesting expression to get out, all right? One last thing I want to talk about is in terms of sort of analyzing this expression and bringing it to things that we saw earlier in the semester, okay? Is I made the point in this discussion that we've been having, right, that temperature does affect all of this. Temperature affects mu, temperature affects G, so temperature affects K. All right. And remember, we're saying K, we kind of mean KP there, but everything we say about KP and these arguments that we're making, they apply to any K, any Q, all right? And like I said, we'll talk more about deviations from ideal behavior in the next video. We know that temperature affects K. We know that as we heat something, as we cool something, the equilibrium shifts around, right? That's just something that we know. When you actually saw it with your borax lab that you did earlier in the semester, if you heated borax up to a higher temperature, more of it dissolved. The colder it was, less of it dissolved. So this reaction was occurring, and it changed based off of temperature. So if the equilibrium is shifting based off of temperature, right, then that means that K is changing based off of temperature, right? So if we look at this expression right here that we wrote down earlier, delta reaction G naught is what gives us K. It's minus RT, the natural log of K, right? Definitely true, right? It's better now to introduce dependency. So a lot of you looked at this sort of expression earlier in the semester and you said, okay, well, there's T. That must mean that that's the only thing I really have to change about this, right? To get at what K is at a different temperature. Because there's T as a variable. So it's better, and I'll talk about why that was a mistake, right, unless some assumptions are held. It's better to kind of remind ourselves, well, delta reaction G naught, it itself depends on temperature, right? Maybe over a temperature range is constant, but it itself depends on temperature. It has a functional form that depends on temperature. That means, right, K itself also depends on temperature. Now, this isn't as nice and tidy, right? And so what we normally do is we drop this temperature dependence because we realize, okay, you guys know delta reaction G naught depends on temperature, so does K. But looking at this, it really just emphasizes that point. It's not just T changing here, but T changing here, right, could also influence what this value is. Just independence of T changing here, this itself might have some functional form. And we actually looked at that earlier in the semester. We looked at how this guy right here changes with temperature, right? And we called that the Gibbs-Helmholtz equation. We said that the Gibbs-Helmholtz equation describes the temperature dependence of delta G. And we looked at the Gibbs-Helmholtz equations for situations where delta H was constant. And we looked at the Gibbs-Helmholtz equations for situations where delta H had some functional form. But for sure, right, this standard value, which gives you your K, has a temperature dependence, right? It has a temperature dependence. So what we can do is we can go back to that Gibbs-Helmholtz equation, right? And now I have a substitution to make. All the arguments we made earlier in the semester about the temperature dependence of that standard, right, delta G naught, we can then apply it to the temperature dependence of K. It's a substitution that we can make, right? So what I'm going to do next is we're going to derive a formula for how K changes with temperature by using the Gibbs-Helmholtz equation, all right? So let's do that. So let's start by writing down the Gibbs-Helmholtz equation from earlier in the semester. It was partial, right? Delta G naught over T, right? Partial T done at a constant pressure was equal to minus delta H naught over T squared. This is the Gibbs-Helmholtz equation. This is our starting point, right? Remember, we're being lazy here. This has some temperature dependence, and so does possibly this. And remember, that was the big thing about sort of what the temperature dependence of G looks like, what's happening there, okay, in terms of its temperature dependence. So now what we're going to do, though, is, I have a delta G naught here. So that equation that relates delta G naught and K, I can substitute it in right there. Remember that substitution looks like minus, so I'm going to pull the negative out, all right, RT, the natural log of K, but there's still a division by T here. I'm just going to draw it in black to see that it kind of comes down, right? There's still this division in T once we do this substitution here that actually takes this T that's here and cancels it out. So when I do that substitution, right, partial T, over here, nothing really changed. Delta H naught over T squared. When I do that substitution, what I have is, I have an R that I can bring out front. But inside here, what I see is I just have D natural log of K. All right, so let's do some simplification. Do you see how there's a negative here and a negative here? Those can cancel, all right? Let's bring the R that we can bring out to the other side, okay? So I'm just gonna rearrange this a bit. And what we're going to have when those negative signs cancel is on the left-hand side, we're just going to have R D natural log of K dt done at a constant pressure is equal to delta H naught over R T squared. All right. Again, the negative and the negative cancel, bring the R to the other side. We can solve this first order differential equation. We know that we can write this as D natural log of K equals delta H naught over R T squared dt. And this applies for isobaric conditions or applying an isobaric change, which kind of makes sense because remember what we're trying to do. K is related to standard Gibbs energy. This is standard, right? Delta H. So we're always kind of going to be analyzing these situations at 1 bar. So isobaric conditions, right? Those define what our K is, all right, 1 bar does. We can now integrate this, okay? So on this side, what we're gonna get is a natural log, and I'm gonna write it like this, K at T2, right, minus a natural log of K at T1. Like I said, we're just gonna kind of integrate both of these sides, all right? Over here, when I do this integration, I really don't have any other simplifications I can make. I'm gonna make that point by kind of just writing out all the details. This integral will be between T1 and T2. Check to make sure you can see that. Okay, good. Delta H naught, we remember, is possibly a function of temperature. So it's not something we can necessarily take out of this integral. All right. So what we're left with on the right-hand side is really no change. All I did was add in integration limits and remind myself and you guys that it's a function of temperature. So take a look at this powerful equation. Say I want to know how K changes, right? Say I want to know how K changes. Well, here, if I know what it is at like my table temperature and I want it at a different temperature, what do I need to know? I need to know the temperature dependence of, all right, the enthalpy. Right? I need to know the temperature dependence of the enthalpy. Real crazy, real important, real interesting result. Now, I want you to think about this. We did talk about Le Chatelier's principle in general chemistry and how adding energy and subtracting energy affects different reactions depending on an endothermic or exothermic delta H. And you can actually do that analysis with this expression, okay? I'm actually gonna have you do that for homework. Kind of relate this to our Le Chatelier's principle ideas of how we look at this and how K changes, right, based off of, all right, this delta H naught. I think I'll have you do it for homework, all right? But like I said, it's a connection you can make. So it's a really important equation. Let's derive an equation that you have seen before by making an assumption. So let's take this equation, all right, and let's make the assumption, right, now, so this equation that we're going to write next only applies under certain conditions. Let's assume that delta H naught over this T1 to T2 range, right, is a constant value. Let's assume that it doesn't have any temperature dependence. Then I can go ahead and I can bring it outside the integral. And I can do, right, the actual mathematics associated with this integration of dt over t squared. And what you should be able to come up with mathematically, because it does fit, all right, with math we've done before, is I can combine these natural logs here. You're going to get the natural log of k at t2 over the natural log of k of t2, k of t1 inside there, right, as a division. K of t2 divided by k of t1, then take the natural log, just using our natural log algebra there to combine these. When delta H naught is brought out front, what you end up getting is minus delta H naught over R 1 over T2 minus 1 over T1. And this is an equation you saw from general chemistry that describes the temperature dependence of K. But what I want to really point out here is that this that we gave you for the temperature dependence of K, okay, this assumes that delta H is not a function of temperature over that range, just like your lab did, okay? So again, some really important results that we get here. This is definitely a good equation to know, but as always, remember, this equation came from this assumption. So think about how you would use this equation. You would use a delta G naught to calculate, like, at your table temperature, all right, what K is. Then I want K at a different temperature. I use my table delta H naught because I'm going to assume that over this range, it's going to be the same. So I use my table delta H naught and I calculate that, right? Throw it there. I pick a temperature that I want to change to, and I'm going to see how K changes. So I have everything I need except for that. And so then I throw all those numbers in there, pay attention to units and significant figures, and I analyze this just like you did in general chemistry. Okay? So again, we developed a lot of equations here. Make sure you understand how to derive them and analyze them. So those are two important steps that are needed. Know how to take something like this and this, or any other equation that we derived, and throw actual numbers into it using the skills you've already developed, and then be able to come up with a numerical value for any of these variables and then interpret the results correctly. Okay? So it's more of what we've been doing all semester. What we're going to talk about next is everything that we've talked about so far. We were able to develop all these general sort of things that we're saying about ideal gas Ks that came from ideal gases, and Qs that came from ideal gases. And it turns out that all of this is generally applicable with minor corrections for other systems that we're going to talk about, other important chemical systems that are important to us. Okay? And like I said, we'll get into that more next time.